Let's look at this isotopic symbol and decode every little detail. This gives information about the numbers of protons, neutrons, and electrons in an atom or ion. So first I want to talk about the atomic number. In the case of our example, the atomic number is 53. It is often given a variable of capital Z, and it is equal to the number of protons in the nucleus. So in our isotopic symbol, it's going to be a subscript before our elemental symbol. I'm abbreviating the elemental symbol as E, but that's a variable. This atomic number is also completely and totally redundant, so you do not actually always see it written. Let's look at the periodic table to figure out why. Elements in the periodic table are in order based on their atomic number, meaning they're in order based on the number of protons in the nucleus. Hydrogen is element number 1, and all hydrogen atoms have 1 proton in the nucleus. Helium is element number 2 with 2 protons in the nucleus, and our example is iodine. Iodine is element number 53 with 53 protons in the nucleus. So why do we bother writing a 53 there sometimes if it's redundant? The answer has to do with if you go on to write nuclear reaction equations, having the atomic numbers there make figuring out missing products or reactants as simple as an addition or subtraction problem and looking up the atomic number on a periodic table. So in this reaction, if you look at the atomic numbers, you see 53 equals 54 minus 1. So I really recommend wrapping your head around these isotopic symbols if you need to eventually learn about nuclear reaction equations. The next thing I want to talk about is the mass number. In our example, the mass number is 131. So it's written as a superscript before our elemental symbol. It's given the variable of capital A. You see it as a superscript before element E. So our example, it's 131. This is equal to the number of protons plus the number of neutrons in the nucleus. You can remember that atomic number is represented by Z and not A, even though A would make a lot of sense because atomic starts with A, just by reminding yourself that sometimes chemistry is pointlessly difficult, and think of some old dead guy rolling over in his grave laughing at you about this variable assignment. This is not redundant. It specifies what isotope we are talking about. Isotopes are atoms of the same element with different masses. The way they can have different masses is by having different numbers of neutrons in the nucleus. So masses of protons and neutrons are so similar that just counting the total number of them gives us a nice whole number mass that we can, once again, use to quickly figure out what isotopes we're talking about in nuclear reaction equations. Look at the mass numbers here. 131 equals 131 plus 0. It reduces nuclear reaction equations to addition and subtraction problems. And masses of electrons are so much less than that of protons and neutrons that we're just ignoring them as rounding error. Think of electrons as lightweight freeloaders. So unlike atomic numbers, this is not redundant. You need this mass number to specify the isotope. If I am verbally saying the name of this, the element actually comes first. So our example is iodine 131, and that's written iodine hyphen 131 with no spaces. So it's verbally said in the opposite order of our isotopic symbol. But from the information we have so far, we can calculate the number of neutrons in our nucleus. So the number of neutrons is equal to our mass number, A, minus our atomic number, Z. So in the case of our example, That is 131 minus 53 equals 78. So far we have figured out that our iodine 131 has 53 protons and 78 neutrons. But we can also figure out the number of electrons in orbitals, and that's based on the charge and comparing that charge to the number of protons. So my example does not have a charge specified. That means it's uncharged, or the charge is 0. If there is a charge, you'll see it written after the elemental symbol as a superscript. So protons are positively charged, and we know the number of protons in the nucleus because it's exactly the same as the atomic number, in our example 53. Electrons are negatively charged, with charges that cancel out those protons. So if we have 53 protons and a charge of 0, that means we also have to have 53 electrons. But our equation to calculate the number of electrons is the number of protons, Z, minus the charge. So in our example, that would be 53 protons minus a charge of 0 equals 53 electrons. If you have a charge of -2, you would have 2 more electrons than protons. If you have a charge of +3, you would have 3 fewer electrons than protons. The charge compares the numbers of protons and electrons. Let's do some example problems. So I have 3 examples up at the top, 3 different isotopic symbols, and for each, let's calculate the numbers of protons, neutrons, and electrons. So pause if you want time to figure this out for yourself. But first we have carbon 12. And once again, for good measure, this would be written as carbon-12. The number of protons, we do not see a subscript here for our atomic number. That means we need to look at the periodic table for carbon. So carbon on the periodic table is element number 6. That means we have 6 protons. Over on the far right, I'm going to be writing variables and formulas. Atomic number is Z. Number of neutrons in our carbon 12. This is our mass number, A, minus our atomic number of Z. So our mass number is given as 12. 12 minus 6 equals 6. And number of electrons, that is equal to our atomic number minus the charge. So our atomic number is 6. There's no charge specified, so minus 0. 6 minus 0 is 6. So our carbon 12 has 6 protons, 6 neutrons, 6 electrons. Our second example is selenium 82 with a -2 charge. Once again, we're missing the atomic number, so let's look at the periodic table. Selenium is element number 34. That means our number of protons is 34. Number of neutrons is our mass number, 82, minus our atomic number of 34, which is equal to 48. And our number of electrons is our atomic number, 34, minus a charge, so minus a -2. Minus a negative is the same as plus a positive, so our number of electrons is 36. And our third example is iron 56 with a 3+ charge. Our atomic number is written as 26, so we don't have to look at the periodic table this time. Number of neutrons, 56 minus 26 equals 30. Number of electrons is our number of protons minus a charge, so minus a +3. 26 minus 3 is 23. So our iron has 26 protons, 30 neutrons, 23 electrons. And for good measure, we can specify atomic numbers, which is the same as our number of protons, just because they're missing here. The next big question is, why are these masses not the same as they are on the periodic table? We were just talking about iron 56, but we can see a mass of 55.845 on the periodic table. That's next. Thanks for watching Chemistry in a Nutshell. If you feel that I've earned it, please like this video and subscribe to my channel.